All right, guys, we are making our way through Unit 1 and we're starting Chapter 3 now. And Chapter 3 is where we get into really talking about numerical distributions, how we display numerical distributions, how we describe them. And we're going to be a little more precise in this chapter about describing the measurements we talked about, the characteristics we talked about in the previous chapter. We'll get a little more rigorous with that now. So make sure your cell phones are put away, that you're ready to focus for the next few minutes. And I want to start out by talking about symmetric distributions specifically. How do we work with symmetric distributions? There's two main things we're going to use to describe a symmetric distribution, two main measurements, I should say, to describe a symmetric distribution, and that's the mean and the standard deviation. Before we get too into that, I want to remind you what are the three characteristics we use to describe numerical data. Well, the first was shape, and we said that that could either be symmetric or it could be skewed, and then with that, it may not be unimodal. We might need to talk about bimodal data. Sometimes that comes up. The next characteristic we use to describe numerical data is the center. So the center is the typical value, or a value we feel really represents that data set. And then the last was the spread, which we could also think of as the horizontal variation. So these two measurements, the mean and the standard deviation, are going to help us describe the center and the spread. So when we're working with a symmetric distribution, the mean is what we're going to use as the measure for the center. And you've probably heard of the mean. I would imagine you did that at some point in high school. The mean is a fancy word for what we would think of as the numerical average, where you add all the numbers together and divide by however many are in your data set. Similarly, when we have a symmetric distribution, the standard deviation is what we're going to use as our measurement for the spread. So horizontally, how spread out is the data? Standard deviation you can kind of think of as a typical distance each value is away from the mean in a given data set. So let's look at a quick example here. So we've got a dot plot for a distribution of test scores. The mean for the data set is 24.2, and I believe that's where this little dotted line is drawn, is at the 24.2 mark on our dot plot. So our lowest score, it looks like, is 18. Our highest score, it looks like, is, I don't know, maybe 35, somewhere in that range, 34. How would you describe the shape of this distribution? Well, it's not perfect, but I hope you would say that it is roughly symmetric and unimodal. It's got the one peak at the top, and it certainly looks to me like it's close to a bell-shaped curve. So I would say roughly symmetric. And let's add in unimodal just for clarity. And so what is a good measure of a typical value, or the center? That's another word, so I'll start kind of using those interchangeably. Typical, center. And in this case, that would be somewhere right here in the middle. If we were eyeballing it, we might say somewhere around 24 to 25, somewhere in there. But because they actually gave us the mean, let's go with that. So my center is going to be the mean, which is at 24.2. Would you say that is a good representation? I would say yes, it certainly is, because I would say just by eyeballing it, the center is somewhere right in this little range, and so 24.2 would work. And that's because the data is symmetric. The mean gives us a good representation of that center. So using the mean to describe typical values. So here's what you want to remember. When the distribution of the data is symmetric, the mean represents what we would consider our typical value, or our center in the data set. When the distribution is skewed, and I think I'm missing a word here, but this should say the median, which we'll talk about later in Chapter 3, is going to be a more appropriate estimate for our typical value, or our center. So as long as the data is symmetric, we can go ahead and use the mean. Computing the mean, now if you have a small data set, you can always add them up. And by the way, this symbol here is called X bar, and we're going to start using that throughout the semester. But X bar is what we mean for the mean of a sample. And one way we could do that is we could just say it's the sum of each value in the data set and divided by n, where n is the number of values in the set, or in the sample, I should say. And you've heard that before. You just add them up and divide by however many there are. Now, here's the good news. I'm not going to ask you to calculate any by hand that I can think of, unless maybe there's a couple and it's just something quick to do in your head. Usually we're going to use StatCrunch to figure this out. And so that's what we're going to focus on in class next time. Now let's talk quickly about that standard deviation again. So recall that the variability in a distribution is measured by the horizontal spread. Visually, how spread out is the data? Why do we need to know this information? Well, it gives us an idea of whether or not the data is spread far away from where the mean is. So is there a lot of variability in the data? Or is most of the data, or are most of the data points close to the center? So we can think of the standard deviation as the typical distance. So let me write that down. The standard deviation we can kind of think of as a typical distance. So you always want to, when you hear the standard deviation, you want to think distance. It's a typical distance each value is away from the mean. So a quick example here, it says we're looking at high temperatures in 2017 for St. Augustine versus Mount Pleasant. So St. Augustine is the first graph, Mount Pleasant is the second. How would you describe the shape of each distribution? Now, I think you could make an argument here that maybe St. Augustine is possibly left skewed. It's a little subjective. You could even say it's maybe symmetric. I'm not sure. It's kind of hard to say. I would say maybe St. Augustine, well, I'll go with left skewed. It looks to me like maybe there's a little bit of tail and then more of the data is on the right side. So we can say left skewed for St. Augustine. And then for Mount Pleasant, looks to me like it's maybe roughly symmetric. It might even be potentially bimodal because of this peak here, and then you've got another peak here. But I would say you could argue this is probably a little bit more symmetric than the St. Augustine graph. Which one, though, appears to be more spread out horizontally? So we could use standard deviation to compare the two, but if we just want to do it visually, one way to do this is to literally look at the range. So the range for St. Augustine goes from about, I don't know, 45 degrees maybe, 48 degrees, something like that, up until about 95 maybe. So the range for St. Augustine is roughly 45 to about 95, eyeballing it, whereas the range for Mount Pleasant, definitely smaller. I would say maybe from 10 to about, I don't know, maybe 90. So I would say visually, you probably would agree with me that Mount Pleasant is more spread out. But one way to kind of do that, if you're second guessing yourself, is to look at the range. And so the range for Mount Pleasant certainly is larger. Now, let's talk about the standard deviation. So the standard deviation, again, I'm going to give you the definition. It's the typical distance. Keep drilling that in your mind. It's a distance. Standard deviation is always a positive quantity. It's a typical distance each value is away from the mean in a sample of data. For most distributions, a majority of the data is going to be within one standard deviation of the mean, and we'll get more precise about what we mean by that later on when we say within one standard deviation. And like I said, oh, here's the definition. I just read my own notes. The standard deviation can be thought of as a typical distance. I just really like that definition and that term. You want to keep reminding yourself that that's a distance. Now, there is a formula for computing standard deviation. It involves a square root and adding up the values, and it's a little bit complicated. I will not ask you to calculate a standard deviation by hand, so you don't need to worry about that. We're going to use StatCrunch anytime we need to compute a standard deviation, or they'll give it to us in the question. Last little thing is the variance. The variance is the square of the standard deviation. Generally, we don't use a standard deviation. We don't use the variance because the standard deviation has the same units as the mean. So that's typically our preferred measurement. But sometimes you'll see us talk about the variance. So I want you to at least have heard of it. One other thing I just thought about, let me give you notation. When you're talking about the standard deviation for a sample of data, we use a lowercase s. That is the symbol for standard deviation for a sample. So the variance would be s squared if we were talking about variance. Don't worry so much about variance right now. And like I said, we'll use StatCrunch to calculate the standard deviation in class. And I'll see you tomorrow.